Ladies and gentlemen, welcome to today's Hong Kong IE Civil Division event, technical webinar on eco-hydraulics and low-impact development in urban drainage systems, organized by the Hong Kong IE Civil Division and the Polytechnic University. I'm Fiona, MC of today's webinar. We are honored to have Dr. Huan-Feng Duan, who is currently an associate professor and the unit leader of hydraulic engineering in the Department of Civil and Environmental Engineering in the Hong Kong Polytechnic University. He is engaged in the research of urban hydraulics and volcanics, including various research topics of urban water supply system and spongy city, river and channels, hydrodynamics, coastal flooding, and climate change. Dr. Duan has published his representative papers in the key journals of his research field, such as Journal of Fluid Mechanics, Water Resources Research, and Journal of Hydraulic Engineering, which has been selected as highlight and prize-winning papers by journal editors. Without further ado, I would like to invite Dr. Duan to deliver the talk. Dr. Duan, please.
Thank you very much, Fiona. So today I would like to share some of my research on this topic. But before that, I would like to share some information about our department. Actually, I would like to appreciate the department and also Hong Kong IE can give me this chance to share this some research information with all of you. So our department actually in the PolyU is there are more than 40 staff currently, and most of the staff actually have already had very high achievements in their respective research fields. Like according to last year, this kind of rankings, if you look at this members, more than 20 or 8 staff have been listed as the top 2% scientists by the Stanford University last year. Actually, this year, even more will be updated soon. And the ranking of this department, like the civil and structural engineering, is also well recognized in the world. Like according to different rankings, it could be from number 2 in Hong Kong or number 1 in Hong Kong, according to different rankings. Anyway. And that is about the research excellence. Like here, we list some of the colleagues in our department who have made very significant contribution to the different research topics, which can be found through these slides, and actually has been supported from the different large-scale research projects by the government, like the RGC and so on. And also the achievements can be briefly summarized in this following slides. Like we have a Green Tech Fund from the EPD to address some low carbon or some sustainable waste management and so on. And also some other research schemes like the some model testing facility for the debris flows in Hong Kong, which actually becomes very critical so far as due to the climate change or the rainfall, and also the impact fund from the RDC to address the drainage or the material problems in the pavement or other aspects. And then we have different programs like the undergraduate programs in the civil engineering and sustainable development, as well as the postgraduate programs and research postgraduate programs in master level or PhD levels. And then we have, of course, we have many very outstanding alumni. Here in this slide, we just show some from them, I'm sure, not just limited to those. Okay. Also, I believe that most of you may be familiar with some or all of them. And then we have also advanced facilities in our department for teaching and also research. And of course, this already got the support from the university and also the government departments, so that we have this kind of facility to achieve the teaching and the research. Finally, here, this is our department website. If you would like to know more or explore more information, you can use this kind of social media channels or the websites. Okay, so that's all for this kind of information about our departments. So this is also the task given by our department head, so that we can share some basic information to all of you, or at least some recent progress or achievements from our departments. Okay, so now let me to start our my presentation. The topic as introduced in the poster or by Fiona just now is about the eco-hydraulics and the LID, the low impact development in the urban drainage systems. Okay, and from this department. And then this is the outline of my talk, divided into several parts. Just to start with some introduction of the background of this topic, especially for the urban stormwater drainage systems and its significance nowadays, and then followed by the some challenge as well as the some developed research and also the achievements in my group. And then finally, give you some summary information or discussion on this topic. So we know that the urban flooding becomes a very global challenge in the world, no matter in the Southeast China, Asia or Europe. In the couple of years ago, like 2021, there are many different regions or countries in Europe or Southeast Asia encountered very severe flooding problems, cause a lot of damage. This can be commonly found if you search from the Google or other social media. And if you look at China, mainland China, in this year, like this one, Beijing, this year, it encountered very huge flooding events due to the very heavy rainfall. And then it caused a lot of problems, including the deaths or some other problems. And some years ago, 2 years ago, we know that there were critical or there were serious flooding events occurred in Zhengzhou, China. It cost around 400 people dead or missing in these events, and of course, a lot of damage, including the economic or other social damage in this city. Now let's see this problem in Hong Kong. We know that just in the past in the some months ago, we have encountered here some huge rainfall or due to the typhoons and then caused the problems. Look at this occurred in September this year, just last month, okay? And then we can find out this kind of rainfall distribution in that events. It actually has some very important observations, and like the peak rainfall can attend to 158 millimeters per hour, and actually this already break a lot of records in the past like 100 or 50 years, and then it's equivalent to 5 years return periods of the rainfall intensity if according to the current calculation or estimation from the HKO, Hong Kong Observatory. And then also there are a lot of problems. Actually, I believe many of you already observed that in Hong Kong. Like we shown here, there's some kind of pictures. I'm sure you already noticed this or actually or even experienced this kind of problems in the recent several months. And then, of course, we have to propose something to solve the problems. So just today, I'm sure you noticed the Hong Kong Chief Executive's policy address this year, and already mentioned this problem, try to improve the stormwater drainage system so as to reduce the risk and also the damage consequence from this kind of extreme weathers especially due to the long-term climate change and so on. Okay, so this is the background of this topic. It becomes very important and also emergent for many different cities, including Hong Kong. So now let's see the challenge of this kind of problems through the engineering and scientific research. Like the engineering, if we're going to construct some measures or facilities to address the problem, we have to consider many aspects like the cost effective or the feasibility of the engineering as well as the complexity and so on. So this is a very common way to consider. And then from the research perspective, we have to understand the mechanism behind any engineering project and also any this kind of extreme events, and also is to propose the suitable and comprehensive framework to solve the problems. Especially we have to consider the long-term climate change and urbanization in different cities, and also have to develop the relevant tools like the models or methods, including the simulation technologies or tools to solve the problems. So according to the research in our group, we have tried to address some of the scientific challenge on this topic, including the models and the methods, as well as some framework to understand and to simulate the process of the rainfall and also the drainage process. So in the urban drainage system, is particularly for the stormwater drainage system, like the coastal cities in Hong Kong, it could be a very complex system, no matter from the disciplines or the series or the system itself. It could be multiple system components in this framework. So it can involve the multiple disciplinary series like the hydraulics or hydrology, also the some flow mechanics knowledge to understand the flow characteristics, and also interacting with the structures in the system or the soil itself. And at the same time, we have to consider the influence factors like the climate, the weathers and so on, and then to propose some scientific computing technology that can be used in this field. And finally, to combining the advanced data analysis methods like the AI or big data, so as to propose some intelligent framework to solve the problems. And then, of course, this drainage system, stormwater drainage system, not only about the drainage channels, it could be consist of different subsystems like the surface runoff, the pipe system or open channel system, river system, as well as the coastal water system if we are coastal city. So it could be a very complicated and complex system to address the issues of the flooding in the coastal cities. So now in this presentation, I'm going to introduce some of the knowledge that will be used to explain some mechanisms of the floodings or even more extreme events during the rainfall process. And then, of course, there are many basic knowledge like the basic hydraulics, including the mass conservation, momentum equations and energy equations and so on. But in addition to that, we have to consider more extreme case like the superposition of different phenomena that can be occurred in the drainage system. It's usually one of the key reasons causing the damage to the system. So the first part I'm going to introduce is about the multi-phase flows into drainage pipes or systems, because during the very fast runoff or drainage, surface drainage, the water goes into the system, the drainage system from the the rainfall collection system, and then it may cause some multiple phase flow, like the air can be trapped or taken into the system. So the air, like in forms of the bubbles or cavities or any other pockets, anyway, it can be contained or maintained in the drainage system, cause some severe problems under the specific conditions. Like when we drainage the water from the surface goes into the vertical collection pipe and then drainage to the downstream with different slopes, and then the air trapped initially goes into the system can be existent in different forms, and also it stays in the different parts could be very different, like the air perkins, or some maybe in the free surface, some maybe in the pressurized, and so on. So this could form as a very important and also difficult problems through the scientific computing perspective. The air-water flows under this unsteady state. So in this regard, the form of this trapped air in the pipe section could be divided into different types for the investigation. There are different properties or the dynamics, like the bubble flow, plug flow, or slug flow, as well as the other different forms. For each of these types, then the treatments from the simulation or from the physics could be different when you're going to simulate or solve this flow in the system. The different method should be used, because some of the method may be applicable to solve the bubble flow, because the bubble flow could be relatively uniformly distributed, while for the slug flow, the relatively separation regions in the pipe can be observed, and then you have to treat the interface clearly. So in this regard, due to this air trapping in the drainage system, it can induce some problems, including this drainage capacities reduction, as well as some extreme pressure change. So the pressure change, like the sudden increase of pressure, it can cause some problem, like shown in these figures. As example, this a kind of the drainage system, the water comes out from the manhole, and of course, due to the high pressure, it could be the pressure of the flow itself, but also it may be due to this the air and the water interaction, especially like this in the first figures. The pressure could be attaining to over 30 meters of the head. So this air inside the drainage pipe can cause very serious problems. So how to address this problem, how to predict, or how to model the system before we can have a very good or better design of the system. So we have done some experiments in the lab so as to understand how does the air propagate under these pressurized conditions, especially under this the sudden drainage or the sudden inflows from the upstream because of the runoff of the heavy rainfall. We have done different experiments in the lab so as to understand the air pockets, how they propagate or pressurized or released from some like the vertical risers. It's just used to mimic some manholes in the drainage system. So like shown in here, this different of the size of the risers. And then, of course, at the same time, after these experiments, we have to further simulate this process so as to know more details, because experiments can show you some basic phenomena, and also you can measure some typical locations values, but you cannot measure all the location or the overall pictures of the distributions of the pressure and the velocities. So the modeling is another useful and important method to mimic or capture the whole process of the drainage. So we propose this to refer to the two-phase models so as to capture how does the airflow air pockets propagates under the different conditions. We can, in the model, we can set up different boundary or initial conditions so that we can understand exactly the process or mechanisms in the system. So from our research, we can find out some oscillations, including the experiments and the simulations, and also different numerical methods, which shows that some of the methods can exactly to show the trend, the very good trend of this oscillation of the high pressure in the system, as well as the amplitude of the oscillations. For example, the 2D incompressible model can exactly to show you the trend as well as the amplitude. However, if you're going to use the compressible model, it seems that from the physics, it may be more reasonable. But if you're going to deal with the interface, it causes a very unstable state due to the numerical oscillations. Not exactly the physical oscillation due to the numerical oscillation because of the compressibility of the air inside this pipe. So it can cause this even larger difference between the experiments and the models. So according to the proposed model we have in this work, we can actually to understand some mechanism or the phenomenon why this kind of air entrapped in the pipe can cause so large damage or so cause this kind of gathers in the system. So this can be analyzed through this numerical results based on some energy perspective. We can easily understand through the simulation that in the whole system, the energy can change or transformed according to or among the different forms like the kinetic energy or potential energy. They can exchange to each other in the system due to these oscillations. And finally, we can understand that during this air water flows, there are huge energy formulated actually under the compressed state of the air, especially when it attends to any release or releasing risers, this energy will be released to form as this very huge water column like we have observed in the former slides. Okay, so it caused a lot of damage in the system. So this is the first part we have done for understanding the air water flow, the role of the air inside the pipe. It can cause very huge energy variations during the draining process. And then another one is when we concerning the drainage in the urban system, it also concerned about the channels capacity for addressing the flooding problems. However, we know that if we have proposed a lot of developments of the sustainable and the renewable systems. So including the drainage channels, we usually to build the channels with the plants or the aquatic vegetations. So in this regard, it can maintain the ecological or ecosystems, but at the same time, it can cause some other problems from the hydraulic perspective, like the reduction of the drainage capacity or even the sediment problems or other hydraulic problems like the turbulence and so on. So to understand or investigate this kind of vegetative flows in the drainage channels also becomes very important for the whole drainage process in the urban drainage systems, because in many urban drainage systems, some parts consist of this type of the vegetated channels. So if you look at the vegetation roles in the drainage system or channels, it may be submerged into the water or emergent from the waters, or partially in the channels or fully occupied in the channels. So it may cause different interaction between the flows and this kind of vegetated sections or the vegetated parts. So how to understand from the flow mechanics point of view, like how does this vegetation block the flow capacity or change the velocity in the different parts in the system, especially can cause some sediments erosion or sedimentation problems in the channels. So we have done experiments to explain the phenomena of the vegetated flows in the drainage channels, including the how does this kind of vortex formed in the system, and also how it influences exactly the flow velocities between the vegetated and non-vegetated parts. Actually, we found that they have some exchange of the momentum between the vegetated part and the non-vegetated part, so that the velocity or the flows in this kind of channels can be greatly affected for its distribution and also the energy loss. So we have measured different velocity to explain how does this kind of oscillation flows and also the vortex formed in the channels. And then also we found that there's some secondary circulations, and this kind of circulation flow is one of the main reasons to cause the morphology change of the channels, like the sediments or the erosions. So like as shown in this picture that we have done in the laboratory, it can found that in the vegetated part that because finally it becomes more and more the sense or the increase of the surface of the bottom. While for the other parts, like the right hand side, there clearly the sense here, the bottom has been eroded a lot or significantly due to the circulation flows between these vegetated and the non-vegetated parts. So finally, we can formulate an equation to predict how does this vegetated part can change morphology or the distribution of the sediments in the channels. Of course, finally, this change after a long time, it can also affect the drainage process as well as causing the flooding, especially within the section of the vegetation patch. So this is the second aspect we have done for some basic research to understand some flow process or dynamics in the channels, in the drainage channels. So this is the equation as I mentioned just now to propose to predict this sediment change in the vegetated part, so that we can make the prediction of this kind of morphology change of the channel bottoms or the bed morphologies along the channels. If we're going to plant some vegetation or plants along the channels. And then now this is the first two parts. I just give you a very simple introduction of some basic or fundamental research regarding the air-water flows and also the vegetated flow that may occur in the drainage process. So this these are about this kind of very basic research. So it could be a very small part of the whole urban drainage system, but it may be very important to the drainage or even the extreme phenomena we have observed. Like this, the key findings from this basic research. Like the first one is the complex flow regions or phenomena like the gathers or the air-water releasing flows in the drainage system can be formed under the specific conditions. Of course, this can cause some damage because of the release through the gate, through the risers or manholes. And then is the vegetation can reduce the drainage capacity in different ways. It can cause this velocity change along the vegetated part as well as the sedimentation problems, especially about the erosion of the channel bottoms due to the circulation flows formed between the vegetated and non-vegetated parts in the channels. So finally, we know that the nature-based solution becomes very popular, but we have to concern this the influence of these different aspects on the flow dynamics or the whole drainage problems. So this in terms of the ecohydraulics knowledge. So if you would like to know more about this kind of details, like how does the circulation flows formed under the specific conditions, how does the flow affect the sediments along the channels with the vegetations, you can refer to the papers we have published recently. And then, so we know that these different factors like the air or vegetation can change or modify or affect the efficiency of the drainage, but how we design exactly the system to avoid the floodings. So the third part is about the green-gray infrastructure for the low impact development. So one of the keywords in my topic is the LID for the low impact development in the urban drainage system. So it can also refer to sponge city or other sustainable drainage system and so on in different regions or different reference. So green-gray infrastructure actually, they commonly exist in different cities. Like in Hong Kong, we have different gray infrastructures to store the stormwater during the very extreme rainfall events, like this kind of detention tanks under this soccer field or under the some other place, Happy Valley storage tank. And then also we have some other deep tunnels to divert their flows under the different conditions. So then it's about the green infrastructure, which is including different LID measures. Like in Hong Kong, we have the permeable pavements so as to release the peak flows under some specific rainfall events because of this permeable pavement materials. There are many other types of the LID measures, like the green roofs or bed retention cells and so on. So each of them have different purpose, like to reduce the peak flow or to control the water quality during the drainage process and so on. So how to design or better design this green-gray infrastructure for the LID implementations in the urban drainage system? This is the topic for this part. So the impact factor on the urban drainage system, we know that the mainly consist of these aspects. Like one is the climate change. For example, we have different rainfalls due to the different climate conditions or weather conditions, like the return periods, the intensity or the peak flows for each of the events. And then is the urbanization, because the urbanization can change the land use or the other aspects. It can cause some of the runoff or drainage process becomes very different from the original design plans, because the stormwater system usually designed and constructed before the urbanization process. And then also due to the economic or social economic development of the cities, like the GDP development, it can actually influence the climate or regional weathers and so on. So let's see the common LIDs we have usually designed for the practice, like the pavement, the permeable pavement, also the rain gardens, the green roofs, and so on. So now here we take these four common used LIDs, for example, to understand the functions or effectiveness of these measures on the flooding issues as well as the other aspects. So for example, if we take this by retention cells for the demonstration of this drainage process. The water initially collected from the surface, it goes into these cells or these parts, and then from the surface layer, it goes into the middle soil layer, so that the water retained in these parts rather than to run through the whole surface. So then the surface flow or runoff peaks will be reduced due to this filtration or the retention effects of this cell. And finally, the water stored in this cell must be also drained into the systems finally. But with these retention effects, then the flow originally collected from the surface its peak flow will be reduced, but the total, of course, total volume is conserved. It cannot be reduced, or the quantities of these waters. And then if we're going to model this system in the drainage process, we have to consider different layers. How does the flow passes through the different layers? And of course, the main purpose or the principles used to design or model this one is due to the conservation of the mass, because the total mass collected from the rainfall is conserved, including the retention part and also the runoff parts. And then for a case study, because if we're going to investigate the effect, we have to take one of the cases to study their exact functions and also the effects on the rainfall runoffs and the peak flows. So we take some of the regions like this, the rare case from mainland China, and we can use this case to study different types of the RID measures, like the green roof or the bioretention cells or the other measures. So anyway, this is just our system taken as the examples. We can take any other cities or the regions for the example, but the framework we developed here should be the same. So if we apply this different kind of the RID or green infrastructures from the RID measures, we can find out different results. For example, through these simulations, we can find out each of the single measures or each of the single green infrastructures have different effects on the reduction of flood volume. So for example, we take these 4 types of the measures. We can find out under the different conditions, their reduction effect also very different. For example, for the relatively small rainfall events, like the 3-year return periods rainfall intensity, we can find out the reduction effect could be attained to like the 70–80%. For example, if we place RID practice with 40% here, we take this as the example, it can attain to 75% of the reduction of the flood volume could be very significant to the flooding mitigation effects. However, if we compare this with the 100-year rainfall events, still we take the 40% for the comparison, we find out the reduction effect becomes much smaller than the former case. So this clearly demonstrates that this kind of single green infrastructure can reduce the flooding effects, but it mainly functioning for the relatively small rainfall events. For the very serious or extreme rainfall events, its reduction effect becomes much smaller. So that's just because of the configuration of each of the green infrastructure, because it's just like this by retention cells. Its volume could be relatively small, and due to these different layers, its flooding or the flowing process becomes relatively slow. So for this relatively small rainfall event, it can store the water and reduce the flooding volume greatly. But for the very extreme events, because of very huge peak flows, the stored volume compared to the total volume could be relatively small. So this kind of single green infrastructure placement strategy could be more effective for the common or relatively small rainfall events rather than the very extreme cases. Now, if we consider combined, for example, we put all these different four types of the measures or infrastructure together to understand whether this combined strategy is more effective or not. Then, through this case study, we can find out the results that even for different distributions of the RID measures, we can find out its reduction effect also has the similar trends to the former single green infrastructures. That is, the flooding reduction effectiveness becomes more significant to the relatively small or mild rainfall events than the very extreme cases. However, if we consider the different distribution, for example, we put all these RID measures in the upstream, relatively upstream of the drainage system rather than the downstream, or uniformly distributed along the whole distribution system, then we can find out the distribution of the uniform becomes even larger than the other cases. So we can find out for different combination or different cases, rainfall cases, the effects becomes slightly different. But overall, compared with the former case, the single green infrastructure cases, the difference becomes relatively smaller because each of the this green infrastructure could be combined together. And then finally, its reduction effect becomes more or less similar if we put this different kind of combination into the system. But if we look at the cases for the very extreme rainfall, we can find out the uniform case. That means for these LIDs, combined LIDs along the channels uniformly, we can find that its reduction effect becomes even more than other cases. So this, at least for this the case study, the uniform distribution becomes more effective for the extreme case. But this may not exactly the same for the common or relatively small rainfall cases. Now, if we look at the reduction effect, we find out the green infrastructure is mainly effective or valid for the relatively small or mild rainfall events. Now, if we're going to have the extreme rainfall case, how to address the problem? So then we have to propose some other optimal RID systems, including both the green infrastructure and gray infrastructure. Because gray infrastructure, you could have the larger storage capacities in the city. So combining these two may have more effective influence or reduction effects on the drainage system. So this is the framework we developed for combining different types of these measures or infrastructures, including the green or gray infrastructures, so as to make this design to be the optimal for the different extreme rainfalls. And then again, for the same case study we mentioned earlier, we designed different objectives for the optimization, like we have to minimum the cost because we cannot construct anything in our urban regions. Sometimes if we're going to construct some gray detention tank, it may cost a lot, especially some downtown areas. And then we propose the second objective, of course, to minimize the damage caused from the flooding so as to maintain or mitigate the flooding effects. Finally, it's about the resilience. If we cannot avoid or to eliminate all the flooding problems, but we have to make sure the system resilience becomes better than the original design. So this is the three objectives for the design of the LIDs, considering different functions of the LID measures, including the green infrastructure and the gray infrastructure, mainly the detention tank. So we have some constraints for different array case. For example, how large of the detention tank we can construct it, or what's the cost it has. And then when we estimate the cost for the damage, we have to consider in the different ways. For example, we have to consider the construction of different gray infrastructure, or what's the damage caused by the flooding. So this, of course, is case dependent. For this case study, we have adopted this local criteria for estimating the different damage causes. And of course, we not only for design for the current state, we have to estimate what exactly the cost for the long term, like the different return period, or what's the life cycles for the design. And then for the resilience in the urban drainage system, we consider this the index. One is due to the severity of this flooding problem in the system, like the duration as well as the total volume and so on. And then is the can cause that by the sustainability index, including the volume of the infiltration or the final storage in terms of the total the rainfalls and so on. So this is different index we assigned to evaluate the designed storm water drainage system for the given conditions. Given condition means for different cities may have different index values. So then is some other values for this case study, like the land use. We must know the land use in the city so that we can design or plan a different green infrastructure in the city for under the given constraints or limits. And then is the other condition we have for this case study. It's of course case dependent for the study. And then finally, we got the results just to show you that if we apply the proposed framework we have, you can get a different design schemes, especially based on the local criteria like economic or the cost estimation we just show you in the former slides. You can find out that some optimal designs based on different criteria. For example, the selected optimal design shown in these figures gives you the different dependence of the scheme. For example, there's the black line curves shown in these two figures. Actually, it's showing that if we are going to focus more on this different causes or the resilience, you can find out overall with different ways of the different parts. This is the best design under these scenarios. Okay, so for different scenarios, you may have different design schemes, but even for the same scenarios, you can get different design schemes with different costs or other results. This can be useful for the decision making based on the dependence of factors. And then here is the selected results based on we proposed these different factors like the resilience, reliability, or sustainability, and also the peak flows. We assign the different strategy of the weight. We can get different scores, like the for example, the first one, they're ranking the number one under this current condition we have is the scenario 2 with this different design. For example, the cost could be relatively higher, but the flooding issues or the outlet peak flow could be slightly higher than other schemes. For example, if we're going to focus more about the peak flows to try to reduce the peak flows in the system, then you have to pay more about this cost initially. So then this based on the different decision policies in different cities. But anyway, this framework can provide you this choice for the given conditions. And then again, to show you that this method can show you different response from the selected designs. For example, if you're going to select this scenario 2, you can find out what's the effect of the different factors, the reliability or sustainability, which one is more important, or which one is more preferable in the system. Like this scenario 4 and 5, the sustainability maybe is better than the scenario 2. However, the total cost may be higher than the scenario 2. So this is therefore the different selections. So from this aspect, we can find out some results, or can give a summary of the key findings. The gray infrastructure actually behaves more effective than the others, than the green infrastructure, especially under the extreme rainfall. Okay. In other words, the green infrastructure may be more effective or more feasible for the common and mild rainfall effects. And then is the combined strategy maybe is the better way to consider the different rainfall intensities, or to provide the mitigation effects of the flooding effects in the overall drainage systems, especially when we considering the different factors like the climate change or other uncertainty problems, which will be introduced later. Okay. So the last part is the climate change or the uncertainties. We know that the climate change with the uncertainties in the long term, short term, or medium term. So how does this condition will influence the design of this open drainage systems? So we also propose this methodology framework to understand the optimal design under the given conditions, including the climate change and uncertainties in the system. So especially we select different climate conditions to project the rainfall conditions with the uncertainties, so that we can better understand the robust the functions of the design schemes, or to predict of the future scenarios in the system. For example, we have adopted these different general circulation models to model the climate in the different perspectives, like the short term, long term, and the medium terms, and so on. So based on these models, we can predict the rainfall from this different stage, like the near future, just within 20 years, or the mid future, this like in the other 40 years, or the far future to the end of this century, so that we can predict this rainfall with the uncertainties, of course, because based on the different economic developed prediction, we can have a range of these rainfall intensities for different stage. So we can include this uncertainty or variations of the climate-induced rainfalls into our design framework. And then we can find out the results is based on the given conditions we have for the case study, and including these uncertainties or variation of the rainfalls, we can find out that under the scenario of the economic development, we can find out that the percentage of the damage caused in design for the design, including flooding and so on. And then it could be changing with the different uncertainties, for example, near future, middle future, and the far future. We can find out, especially for the long term, it can produce a relatively larger damage because of the increasing trend of the rainfall effects as well as a larger range of the variation because of the uncertainties of those predictions. And then for the other aspects like the resilience index could be a different or updated way, because if there are more rainfall in the future, its resilience of the current design of the urban drainage system becomes lower. So this is actually updated trend which presents the similar reasons from the former total flooding course. And then finally is the peak flows. If we compare different return period of rainfalls or the different scenarios of climate change induced rainfalls, we can also find out with the peak flow induced in the drainage system can be increasing a lot due to the climate change, and also but the variation compared with the former two cases becomes relatively or more or less constant, because the peak flow is just one of the values from all the cases. So it's automatically to choose the maximum effect from each of the case. So its uncertainty due to the uncertainty of the rainfalls or the climate remains relatively constant even under different return period of the rainfalls. So this is the key findings from this part, that we can include these different influence factors, including the long-term climate change with the uncertainties into our design framework, so that we can achieve this optimal or optimized design under the given conditions. But the numbers we have in this case study, just to show you that maybe not valid for all the cases, but the framework we designed could be useful to estimate what's the variations of the uncertainties, or what was exactly the trend of the flooding issues in the urban drainage systems. So that's actually all the 5 parts I would like to share with you in this presentation. Maybe each of them just very briefly to give you the framework and the final results, but I did not explain exactly each of the steps used for the modeling or analysis. If you have interest, you can refer to many of the reference or ask questions. I will try my best to explain those process. So finally, this is some conclusions or summaries. Of course, just very general ones, which maybe not for those specific case studies. But we know that this is increasing as global challenge from the drainage problems, including in Hong Kong, especially in Hong Kong because of the compound effects like the coastal storm surge and the urban runoff of the rainfall together. They have a compound effects on this kind of flooding problems. And then is to show that the importance of incorporating the hydraulics or some professional knowledge in the design, so that we can predict or expect the extreme cases like the gatherings or those very dangerous phenomena in the system, and then to develop comprehensive strategies so that we can mitigate the flooding effects under the many different conditions, not just for the single or specific extreme conditions, including the green-gray infrastructure development, or for the coastal cities. We usually combine this green-gray with the blue infrastructure, like the receiving bodies, including the oceans and so on. So finally, just to emphasize those kind of analysis is important to make the decisions or management for the flooding issues before we construct or design any systems, or even before evaluate the risk in the system. We need to have some comprehensive framework for the analysis. So this finally is the reference we have mentioned for each part. If you have interest you can refer to some of the reference, or you can contact us for any details. All right. So actually, this is the all content I would like to share. But finally, I would like to also some slides to show you that what there's some ongoing project relating exactly about the urban flooding. So like the first one is the one of the project we have currently to investigate the coastal urban flooding under climate change from a different perspective, like the different mechanism of the flooding caused by the different factors. And then is to propose some intelligent framework for the prediction or forecasting the risk in the system, combining the storm surge and include induced by the typhoon or other extreme events. So then finally, our target is to propose some framework to generate the flooding map in the cities under the specific conditions. And then the second one is we have also some project to install this radar system so that we can monitoring more data, including this rainfall or extreme flooding problems. But of course, this kind of radar network can be used to predict or to monitor more other effects, not only about the flooding. And finally, it's about the tropical storm resilience system in the coastal city, taking the Hong Kong as the example to understand how does this extreme events like the typhoons or other tropical storms influence the cities, like the infrastructure of the city, the high-rise buildings, and so on. So these are projects in our departments. So that's all. Thank you very much for your attention. And if you have any question, you can input into the, I think there's some chat box or answer, ask and so on. Thank you very much.
Thank you, Dr. Duan. We will now proceed to the Q&A section. Please feel free to leave a message to the chat room if you have any question regarding the webinar. The first question we have here is, you would like you to share today's PowerPoint presentation at PolyU's website. Would it be okay, Dr. Duan?
I think so. No problem. Of course, I would like to. If you want to the PowerPoint, I think maybe if I'm going to share this, I have to ask our department to do this. If you would like to just get the PowerPoint, you can send me email. I can send to you, to you. Yeah.
Okay. Then the second question is how to solve the problems of air trapped in drainage pipes in order to minimize its impacts during extreme weather conditions.
Oh, that's a very important question, actually. So that's why we did some scientific research first to understand the air behavior trapped in the system. It's actually very complicated, no matter from experiment, modeling, and so on. But of course, to minimize, sometimes we usually say that we can to install many kind of like the vertical risers to release the air. However, through our research, this is useful, but not always the way to minimize the impact. Yeah, the impacts, because we have to make sure that the air can be released in the proper way. Otherwise, it may cause other problems. For example, if the air, like the release air size is not that large or is too small, it can cause even larger problems because the air can reach those air releasing locations and then cannot be fully released. Then some can be compressed further. So this is also some kind of problem can be caused. So this is no exact answer, I think, but we think that this ventilation is one of the way to release the air, but we have to design this properly.
Thank you, Dr. Duan. The next question is, from observations, fallen leaves covering the gullies have prevent free flow of surface runoff to enter the drainage system. Apparently, this kind of phenomenon has not been properly addressed in the planning and design of drainage system. Any preliminary thinking of how to resolve the said problem?
Oh, yeah, this is very important. I think in practice, this is a very common phenomenon, I think. But I'm not sure whether there any good way to solve this problem. But I think this is more like some management way to make this kind of solutions. I'm not sure from this kind of research or hydraulic problem.
The next question is, with reference to the recent severe flooding in Hong Kong under the Black Rain signal, it seems that the concept of spongy city cannot be applied to Hong Kong in practice because the rainfall intensity is so high over a long duration. What is your view on the above?
Yeah, actually, I also agree with your view that this spontaneity or LID concepts, especially about only the green infrastructure measures, and as I mentioned in my research, they are mainly useful for the relatively small or mild rainfall event. But as you mentioned, under the black rain signal, these very extreme rainfall events, it cannot be used to solve the problem. So based on our research, is that combining the gray infrastructure like the detention tank or the other large energy system may be the useful way to address this kind of problem. So this that's why we mentioned that the green-gray infrastructure combination strategy may be useful to address this kind of extreme events. But we have to say that spontaneity is also useful because this kind of extreme cases are not always every day. So most of the rainfall is just very common and under the control intensity. So the green infrastructure is still working well.
I guess we only have time for our last question. Apart from rainfall, there are theories to prove that huge flood will occur when the Earth axis shift, which is happening. How to deal with huge flood caused by tilting of Earth axis?
Oh, this is a very big question. Actually, I'm not expert to answer this question, I think, because I think this maybe is more concerning me more than the basic hydraulics or hydrology problems. I think that maybe it's more like the earth science or other problem. But so I'm not sure whether I can answer this question.
Thank you, Dr. Duan, as the speaker of today's webinar. We have prepared carbon credit certificates for you as a token of thanks. I'm sure all of us have learned a lot tonight, and I hope you all enjoyed the webinar. The digital attendance certificates will be sent to your email in 4 weeks. Once again, thank you very much for joining the webinar today, and we wish you a good evening. See you all again in future events.
Thank you very
Goodbye.
much. If you have any question, you can send me email anyway.